So continuing our discussion of various numerical methods for solving differential equations, here we'll talk about the midpoint rule. It has second order accuracy, which was higher order accuracy compared to Euler. After viewing this video, you should be able to write a computer program to solve a first order ODE using the midpoint rule. And in addition, you'll be able to explain the advantage of the midpoint rule and disadvantages over Euler's method. Again, the midpoint rule is second order. It has second order accuracy. Now recall that we're solving a first order equation of the form that y prime, the derivative of y with respect to x, is some function of x and y. Now, so we're given the derivative of the function as a function of x and y. We're given a derivative of y as a function of x and y, and we're asked to solve for y. So in terms of derivatives, the Taylor series gives an exact solution for y at some point x sub n plus 1 relative to another point. So again, we're dividing our domain into discrete points, and the Taylor series will give the exact solution at x located at point n plus 1 relative to the previous position. So that's y at x sub n. And the Taylor series is y of x at point n plus 1 is equal to y at point x sub n. With this notation, this is the exact solution, plus the first derivative evaluated at point x sub n times the step size, h, that's the difference in position between point n plus 1 and point n, plus the second derivative of y evaluated at our reference point times h squared. And I'm going to start writing my h's as cursive h's so I can distinguish h from n. And we have the second term is divided by 2 plus our higher order terms. Now you'll recall that Euler's method gave the approximate solution with the first two terms. So let's rewrite the exact solution as y again at position xn plus 1 is equal to y at xn plus the first derivative times h plus a remainder which was of order h squared. Remember, we could describe the remainder as the second derivative evaluated at the right point between xn plus 1 and xn, such that it perfectly described the remainder. So Euler's method used these first two terms, okay? And therefore, the local truncation error was E sub n is equal to the remainder, which was of order h squared, and the accumulated truncation error was big E sub n, and that was of order h. So higher higher order approximations are more accurate. So it's desirable to examine some higher order methods, and they use more terms in the Taylor series expansions to achieve that accuracy. They use more terms in the Taylor series. So let's look at a higher order method, that being the midpoint rule, and it will include the midpoint rule will include the second derivative term. So let's look at y double prime. Let's look at y double prime. So again, y double prime is equal to the derivative of the slope, which is f. Remember, f was the right-hand side of our differential equation, and that was equal to the slope, and that was at point x, and y, which was also a function of x. And I'm going to write this in a slightly different way that will come in handy later. We're going to use this way of displaying the second derivative later. And that's equal to the partial of f with respect to x plus the partial of f with respect to y times dy dx. So this describes the full rate change of f with respect to x. There's a part that's only a function of x, and then there's f changes with y, which is also a function of x. And we can also write that in slightly different notation as the partial of f with respect to x, and we're evaluating that at point, I'm sorry, getting ahead of myself. The partial of f with respect to x plus the partial with respect to y times f, where again y prime is equal to f. Okay, and this is y prime. And so I'd like you to keep this equation in mind. Again, we're going to use it subsequently in this lecture. So to include this term in our Taylor series expansion, we have our first approximation, which is the value at position x sub n plus y prime evaluated at x sub n times h plus the second derivative evaluated at xn times h squared over 2 plus our remainder, which is of order h cubed. Okay, so we're going to second order, so our remaining term for our truncation error will be of order h cubed. So we'll truncate by ignoring the remainder. And this gives us our approximate solution. And the approximate solution we'll write is y sub n plus 1. This is our our approximate solution. And this was our exact. And that's equal to y evaluated at point n, y sub n, plus f, which again was our derivative at evaluated at x sub n, y sub n, times h, plus 1/2 times our second derivative, which, as we wrote out here, is f partial of f with respect to x, evaluated at our reference point, plus the partial of f with respect to y at our reference point, times df dy dx, which is just f. And this is multiplied by h squared, and again this is y double prime. And just for reference, I'll remind you that this was Eulers. This is the part that Eulers Method kept. But here we have a higher order term, and therefore our truncation error, little e sub n, is of order h cubed, and the accumulated truncation error, capital E sub n, is of order h squared. So this is a second order method. The accuracy at some arbitrary point is characterized by this accumulated truncation error. But you'll note that now we have to evaluate three functions. Not only do we have to evaluate f at a given location, we also have to evaluate fx and fy. And there's computational expense to that. So it's desirable to reduce the number of functions that we're evaluating. So let's reduce the number of functions. And we'll do this by taking a step backwards. So we were looking at, we're starting at point x sub n. Before we were looking at the solution at x n plus 1. Now let's look at the solution at x n minus 1. So the complete solution at x n minus 1 is equal to y sub x n plus the first derivative, and our step is minus h because we're stepping backwards, right? And then we have our we have y double prime times h squared divided by 2, and stepping backwards doesn't change the sign here because we're squaring h squared. Minus, so that's just to clarify that that's minus h squared plus our truncation, well, the remainder, which is of order h cubed. And again, rewriting the solution at the forward point, x n plus 1, we get something that looks very similar. We've looked at this before. And you'll notice that if we were to subtract this first equation from the second, we're going to eliminate the second derivative term. So we have y x sub n plus 1 minus y x sub n, and we're also going to eliminate this, the first term, the approximate solution at y sub x sub n, and we'll get the difference being y prime x sub n times h, and it's multiplied by 2, because if we subtract a negative number, we get, it's a sum. And so the midpoint rule turns out, and we also have the remainder part, the remainder of the difference, which is also of order h cubed. So the midpoint rule is the approximation to this, which is y sub n plus 1 is equal to, and I forgot to put y sub n minus 1 up here. I'm just noticing this. Okay, back to the solution. So y sub n plus 1 is equal to y at n minus 1 plus 2 times y prime, evaluated at xn, yn times h. And this is the midpoint rule. So even though we no longer have this second derivative in here, we included it in our derivation. So it's still of order 2 accuracy. So it's second order. It has second order accuracy. And by second order accuracy, I mean that if, let's draw a sketch of how the solution depends on step size. So here we have the exact solution. And let's say we look at different step sizes, h. So Eulers method, if we started off with some certain sized h, it was a first order method. So if we were to half our step size, our error would be reduced by about a half. We'd approach the solution by nearly a half. And the plot of the numerical solution versus the exact solution, well, the plot of the numerical solution versus h would be approximately linear, and that's for Euler. But for the midpoint rule, since it's second order, we might start off with a different solution at a large value of h. But if we were to half h, our error would be reduced by a quarter. So if we were to plot h as a function of, y as a function of h, we'd get a curved function that is of order h squared. Or I should say, approaches, the error is of order h squared. I should say this is, the error is of order h squared. Well, and I'm just noticing that y prime is equal to f, so it would be more appropriate to write the midpoint rule as yn plus 1 is equal to yn minus 1 plus f, evaluated at the midpoint xn sub y, xn and y sub n times 2h. So now the midpoint rule, let me go ahead and write it down so we have it here. Yn plus 1 is equal to Yn minus 1, 2 steps back, plus the slope evaluated at point x sub n, Yn times 2h. So this looks a lot like Eulers. But the key is that the slope is evaluated at the midpoint between x sub n plus 1 and x sub n minus 1. And one easy way that I use to remember the midpoint solution is we're basically approximating the slope as a finite difference, and this word comes up in finite difference methods because we're taking finite increments of x, and we're approximating the slope y prime, which is equal to f at xy is equal to the value at yn plus 1 minus the value at yn minus 1 divided by 2 times the step size. Whereas for Euler, the analogous equation, the finite difference approximation to the slope, would be the difference between y at point n plus 1 minus y at n divided by h. Okay, so this was again first order, and this is second order. So there's the obvious advantage to the midpoint rule is it has a higher accuracy, but the main disadvantage is we cannot evaluate. There's no way to evaluate the function at the midpoint. Or I should say the midpoint right at the start of the calculation. In other words, it is not self-starting. Meaning that if we're given y at point 0 is equal to our initial condition, this gives y sub 1 is equal to y sub 0, and the above equation requires f of x1, x of f2, y2, right? So when that is at the very start of the calculation, n is equal to 2, because we would know that y3 is equal to y1 plus f evaluated at x2, y2, but the problem is we don't know what this is. So that's the main disadvantage. We can get around that by using Eulers' method to solve for y2. So we can address this weakness by using Eulers' method. And to get the same level of accuracy, we'd have to use a smaller step size. Okay, so again, the midpoint rule is of higher order accuracy, and because it's evaluating the slope at the midpoint between two separate points. The main disadvantage is that it's not self-starting, because at the very start of the calculation, when n is equal to 2, we would know what the boundary condition is. That is, the initial condition is that y1 is equal to y0. That's given as the initial condition. And the midpoint rule allows us to calculate the solution 2 steps away from it. But we need to know what y2 is in order to get that that first solution. So we would use Euler's method to find out what y2 is. And once we know that, then we can proceed, and we can continue to change n to 3 in increments of 1 and get the rest of the solutions. We just need a way to start the midpoint rule to get it going. So that concludes the video on the midpoint rule as a second order approximation to an ODE.